Morning all, thank you for dialing into the deep dive webinar on Calix's zero emissions steel technology, also known as Zesty. My name is Christine Gregorian and I look after investor relations at Calix. Before we kick off, just a bit of housekeeping. We've put aside 60 minutes for this session and hope to have plenty of time for questions at the end. To ask a question, please use the Q&A box at the bottom of the screen or email your question through to investorrelations@calix.global, and we will address these all at the end of the presentation. Note that the chat box, hands up, and reaction functions have all been disabled and that this session is being recorded. So without further ado, I'm pleased to introduce the first presenter for this webinar, Phil Hodgson, our MD and CEO. Phil, over to you.
Excellent. Thanks very much, Christine, and welcome everyone. Looking forward to this deep dive into our Zesty technology. Very exciting news recently, obviously, as well. So hopefully this gives everyone a better insight into, I guess, why we're so excited about this recent news and the technology itself. Just a very brief introduction to Calix first, for those who perhaps are less familiar. We have a single core technology that we're developing into multiple different applications. So you can see here, we're targeting cement and lime and iron and steel, which is obviously the Zesty application, but lithium, alumina, we've got a water business, which is also developing some great and growing revenues and margins. So we're quite sort of diversified, if you like, into different industries, but it's all based upon the one core technology platform. Just in terms of that technology platform, what is it? And I can't resist it. I have to bring out the toilet roll. I always do, to explain the core technology. It's a new type of way to heat stuff up. It's a new type of kiln or furnace. What we have is a rather large steel tube, a bit bigger than this. We separate how you heat from what you heat. And how we heat is on the outside of the tube. And so we can heat this tube with traditional fossil fuels, biomass, waste, and renewable electrons. So it's a way, I guess, to heat stuff up that's sort of energy agnostic, flexible. What we heat goes down the middle of the tube. It's going to be a fairly small particle size because effectively we just drop it. And as long as it's smaller than about 1/3 of a millimeter, so imagine holding a lump of dust in your hand and just dropping that to the floor. That's all we're doing in here. Whatever we're heating up, we just drop. It just floats down through the tube over 20 to 30 seconds. And the red hot walls of the tube radiate heat into those particles, and that's how we heat stuff up. So why do it that way? I usually have my rock here, so rock and roll. That's an easy way to remember the tech. This rock is the first applications we started developing the technology, which is for the cement and lime industry. This is a lump of limestone. This is nearly 50% by weight CO2. When the cement and lime industry heat this rock up, it releases that CO2 in the atmosphere. And cement and lime are responsible for about 8% of global CO2, and over half their emissions are coming from that. And so you can imagine with our technology, a different type of kiln, we heat this externally as the limestone particles fall. The CO2 comes out of that limestone, and it's not lost to the atmosphere or to the furnace gases. It comes out the top of the tube as a fairly pure stream. And so it's a way to directly separate the CO2 coming out of limestone. Our chief scientist, Mark Skeets, contacted me in about 2020, thought he had another great application of this core technology. And imagine this rock is red, like a rust iron ore. And he said, look, if we can take iron ore fines and we can introduce hydrogen in the bottom of the tube, that hydrogen loves oxygen. It'll suck the oxygen off the iron ore, which is basically rust, iron oxide. It'll suck that oxygen off and you'll make an iron. And so we had started to develop the idea, and by about 2021, we'd actually filed our first patent on the Zesty application, as we call it, zero emission steel technology. And so there's several other different applications we're developing, of course, but cement, lime, and iron steel, 16% of global CO2. And so one core technology addressing some pretty big global challenges, but that certainly makes us a very big opportunity for us. One area that I'd like to emphasize a little before we head into the talk in more detail energy flexibility. We're very lucky to have Dr. Ingrid Burford here from the Superpower Institute, who'll be speaking a little later on about a recent report from the Superpower Institute concerning a green iron opportunity for Australia. And energy flexibility is one of the things that our kiln is really good at. We've now built our very first what we call direct electrified kiln. We apply a small voltage but high current down this tube, and that heats the tube up. So nothing, no external electric heating like a toaster element. We can actually heat the tube up with a direct current, and that allows us to switch between traditional sort of flames, fossil fuels or burning waste, etc., and actual electrification of the tube itself. That energy flexibility means value, especially as grids decarbonise, they become less stable. The ability to help load balance those grids is a really important development for this particular technology. And I know Dr. Burford will be taking us through the Superpower Institute report and the context under which that creates value. Dr. Burford will cover. So just wanted to emphasise that because that's an important aspect of Zesty. Presenting today alongside me will be Chris, and he'll introduce himself a little further down. But what I wanted to certainly cover off in the first couple of sections here about the significant new milestone that we announced last week, and also a little bit about what's happening globally before we jump into the deep dive with Chris. So just in terms of the announcement last week, you would have hopefully seen that we were able to announce ARENA support for our demonstration project. The first plant we built is capable up to about 500 tonnes per year in terms of its capacity or throughput. This one here, we're targeting 30,000 tonnes per year. And so it's fairly large undertaking. Chris will cover the project in a little more detail further down. The tube or the size of the plant itself is no bigger than what we've already built for cement and lime. But of course, this one's for iron and steel. So this one here will be our first full-scale tube for iron and steel. The ARENA grant was particularly pleasing to announce, 44.9 million for a $90 million project overall. The site will be in Australia, but there's a few options. They remain commercial in confidence while we finalise those site agreements. But very pleased to announce that the grant provides up to 50% of the project capital. It includes some of the commissioning and also test running of the facility. So great step forward for us. Obviously, green iron is important with respect to government policy. Certainly, excellent support from the Australian government. You can see the statement there from Minister Bowen and the support from ARENA as well. And of course, 2 weeks ago, we had the Prime Minister in China with a delegation, including 4 of the largest iron ore players here in Australia. And there was a round table session with the Premier of China on the green opportunity for steel decarbonisation between Australia and China. China producing 50% of the world's steel, roughly. So pretty important. And so it really is technology right in the middle of the opportunity for Australia and obviously with some of our major trading partners like China. The other thing that we'll cover off as we do the deep dive is maybe some comments around, well, is green iron or steel ever going to be economic? The work that we'd done in the FEED study, which was also supported by ARENA, suggested we could start to get a green iron produced into that sort of $400 per tonne range, as long as we had the power down around the 23 to 30 US buck per megawatt hour. 35 to 50 Aussie bucks per megawatt hour. And so we are starting to get into that frame, and it's particularly encouraging with ARENA. Their top priority is to get renewable levelized cost of electricity down to 20 Aussie bucks per megawatt hour. So while there's a way to go there, there's been a 90% reduction in the price of solar power in the last 12 years. So the trend is very strongly in our favour to get down to those sorts of low levelized cost of electricity prices, and that can only be good with respect to where we're going to end up with respect to an economic opportunity for green iron here in Australia. Very briefly, if we have a look at Zesty on the global stage, we often get asked, well, we haven't heard about Zesty. Well, go overseas, you've hopefully heard about us. We won the COP29 award for Net Zero Industry Award at Azerbaijan. We've won the Decarb Connect Award at a Houston Next Gen conference. And of course, even here in Australia, we've been awarded as part of the Heavy Industry Low Carbon Transition Cooperative Research Centre at the annual conference there for work we did with Fortescue, Grange, Roy Hill, and Liberty on green iron. And of course, with all the stuff that's happening around the world, I think there's a lot of focus on the states and which way they're heading with respect to decarbonisation. Rest assured, there's plenty of economies that are heading down the path of decarbonisation. Europe, obviously, one of the key leaders. The ETS or emissions trading scheme being looked at in Europe and being brought in for industries such as the iron and steel industry. And even in Australia, there's a lot of support from the government around, not just ARENA, but the National Reconstruction Fund and these sorts of initiatives. And interestingly enough, just this year, China itself, with an emissions trading scheme locally there for power, have now included cement, steel, and other heavy industry in their own emissions trading scheme. So plenty of economies outside of the US still heading straight down this path of decarbonisation, and that's a great tailwind for us. So on that note, I might move to the next section and invite Chris to join us and take us on a deep dive into Zesty. So perhaps, Chris, if you join us and introduce yourself, and off we go.
Thanks, Phil, and good morning, everyone. It's a pleasure to be speaking with you today about our Zesty technology. I'm Chris. I'm the General Manager for Sustainable Processing at Calix. I'm originally from the northeast of England and then studied in engineering and environmental studies in Sheffield, the steel city. Joined the steel industry in Sheffield in 1999, so I was straight into the melting shop and the world of electric arc furnaces. I've enjoyed 25 years working in the metals processing and heavy engineering industry with roles in operations, project management, and leadership in global manufacturing and OEM companies. Over the past 10 years, I've been particularly involved in green steel initiatives, supporting carbon reduction in iron and steel production. And Zesty is indeed a significant opportunity for this industry. It's well documented that the iron and steel industry is responsible for up to 80% of global CO2 emissions. Iron making contributes to 80% of those emissions, and almost 80% of the global economy has made clear commitments towards net zero. Iron production is expected to transition to low carbon technologies. Iron production is expected to be stable, exceeding 1 billion tons per annum through to 2070. The graphic to the right here illustrates that by 2050, approximately 50% of global iron ore production will be via alternative low emissions technologies replacing the blast furnace, increasing to over 90% by 2070. This presents a significant opportunity for technologies such as Zesty, with strong demand for low to zero emission iron making processes. So as I was saying, the transition's already started, and now is the time to accelerate technical and commercial readiness of low emissions technologies such as Zesty to meet this future demand. There's 4 major iron ore provinces globally. Each region has different ore types and grades. Australia, predominantly goethite, hematite, mid and low grade ores. South America, hematite, mid and high grade. North America, taconite, hematite, and magnetite, mid grade and high grade ores. And then in South Africa, particularly hematite, high grade. Australia is the largest producer of direct shipped ore globally, predominantly low and mid grade ore supplied into the Asia Pacific region. Forecast increases in volumes of DRI and EAF steelmaking routes towards 2050, requiring higher grade input ores, poses a future threat to Australia's iron ore export economy. All major iron ore producers must consider future-facing technology options available to them that have the capability to process a range of ore grades with minimum energy consumption and emission. And this is really the target for all emerging technologies in iron and steel making. Global steel production in 2023 totaled just under 1.9 billion tons, of which 1.4 billion tons was produced in Eastern and Asia Pacific regions. 71% of global steel production is currently via the blast furnace route, and the remainder via the electric arc furnace. EAF process routes typically consume high-grade ores and steel scrap. Blast furnaces historically consume low and mid-grade ores, typically in the form of lump and sinter, however, with an increase in pellet consumption in more recent years. Reducing emissions from steel produced in the Eastern and Asia Pacific regions, in particular in coming years, will have the most significant global impact. Blast furnaces are expected to continue to feed basic oxygen furnace steelmaking processing for some years, given the age of those assets, however, will ultimately phase out. Zesty's got the potential to significantly contribute to emissions reduction in iron and steelmaking by the production of low emission DRI or direct reduced iron and the elimination of major processing steps such as pelletizing. I'll go into more detail on the various processing routes shortly. So there's multiple drivers of a shift in iron production technology. As Phil mentioned before, flexible electrification is becoming increasingly important, and the ability for a technology to avoid high price periods of power can significantly reduce the levelized cost of DRI per ton for future facing technologies. DRI production is set to increase as the largest source of iron to replace blast furnace produced iron. Iron and steel CO2 emissions continue to increase. There's an urgent need for new technologies to be brought online as quickly as possible to help abate those emissions as part of new flow sheets or to complement existing flow sheets to drive carbon emissions down in existing operations. Iron making is certainly the major decarbonisation challenge for the industry, and there's strong government support with positive policy driving the need for green iron, with over 140 companies making net zero commitments towards 2050 and beyond. The significant pools of capital set aside to decarbonise industry, significant volumes globally, and a great deal of movement recently also in Australia. Just looking at the pathways for steel making here, existing iron and steel processes at the top utilise carbon-based fuels for reduction in heating. These processes are currently our largest competitor as we try to bring new technologies into the market. All grades of iron can be produced via a blast furnace, iron making, and basic oxygen steel making. Higher grades, iron units, pig iron and scrap typically consumed in electric arc furnaces. The Zesty process that consumes iron ore fines as feedstock uses hydrogen as a reductant and electricity for process heating. Natural gas may also be used as a reductant, with testing in our existing pilot facilities under planning. Flexible heating can also be considered, as mentioned previously, avoiding periods of high-cost electricity and to continue grid balancing. A number of alternative pathways are also under development that consider different methods and fuel sources for reduction in heating. And examples of that include fluidized bed processing utilizing hydrogen, microwave reduction utilizing biomass, and also electrolysis. Just expanding on the previous slide and focusing on where Zesty fits into the picture here. So as the graphic illustrates, the Zesty process has the potential to substitute sinter and pellet production ahead of feeding the resultant direct reduced iron or hot briquetted iron as a partial feed into a blast furnace. Higher grade iron ore feedstock may also be reduced for direct consumption in electric arc furnaces. Low and mid-grade iron ore feedstock may be reduced without the need for pelletizing and reduction in a shaft furnace for consumption in electric smelting furnaces that are currently under development. For example, in the proposed NearSmelt project, the electric smelting furnace step is necessary to remove impurities from low and mid-grade ores and eliminates the need for high emission blast furnace prior to basic oxygen or electric arc steel making. It's now my pleasure to introduce a special guest, Dr. Ingrid Burford. who's the lead carbon pricing and policy representative at the Superpower Institute. So I'll hand over now to Ingrid.
Thank you very much, Chris. Can you all hear me? Hopefully, let me know if not. My name's Ingrid Burford. I'm the lead of carbon pricing and policy at the Superpower Institute, which is an independent research-based think tank. The work I'm presenting today was designed in very close collaboration with Max van Sommeren at Bivius, which is a sustainable consulting firm. At TSI, our interest in green iron technology is motivated by our broader interest in Australia's green iron and green export opportunity. There are three reasons that a green iron industry would be exceptionally good news for Australia. The first is that the potential is enormous. So if Australia is able to replace its share of iron ore exports with green iron, that is worth up to nearly $400 billion a year annually by 2060. The second reason is that because, as mentioned, steelmaking is such a major contributor to carbon dioxide emissions globally, an Australian green iron industry could abate emissions worth up to approximately 4% of global emissions, which is more than 3 times Australia's current domestic emissions. And third, green iron exports are a natural hedge against the loss of Australia's fossil fuel industries as the world decarbonises. Coal and gas are currently worth about $120 billion each year to the Australian economy. But very fortunately for us, the same progress towards decarbonisation that will depress fossil fuel exports will also lift green exports such as green iron. We modelled green iron production to essentially get a look around the corner, to anticipate what the industry might look like and to gauge the effect of the different policies we wanted to propose. The modelling I'll present today is all based on publicly available information. As with all modelling, we had to make a number of assumptions, but these are very clearly and transparently documented on our website and in the appendices for our report. So I'm presenting this work as a researcher and presenting TSI's results in that capacity. I am not a spokesperson or an advocate for any one technology ahead of another. It is worth clarifying before I jump into the modelling that our work does reflect our expectation that we will be able to produce high-grade DRI in Australia with both low and mid-grade ores, in addition to high-grade ores, obviously, by augmenting DRI technology with electric smelting furnace technology. So what did we model? We modelled green iron production in 5 locations around Australia. So we modelled the Pilbara, Kwinana and Geraldton in Western Australia, Gladstone in Queensland and the Eyre Peninsula in South Australia. These locations were chosen for their access to iron ore, to ports and to good renewable electricity. Each green iron project includes green electricity generation and storage, green hydrogen production and storage, and 2.5 megatons per annum of green iron production based on green hydrogen use. The modelling incorporates 2 types of green iron making technologies. So what we in our report refer to as an inflexible technology, which needs to essentially operate continuously or near continuously. The inputs for that technology are based on existing technologies, and alongside it, we also model what we call a flexible technology, which can more easily ramp production up and down, so it doesn't need that same level of continuity in the supply of renewable energy and green hydrogen. And our inputs when modelling a flexible technology were based on Calix's Zesty. Our model also includes hourly renewable energy capacity for each location and, where available, prices and availability from the local electricity market grid. Of course, we also include capital and operating costs. All of the scenarios that we considered, except for the Pilbara, are modelled as grid connected, and our model includes the cost of shipping ore from the Pilbara around to Gladstone and down to Kwinana. This means that our modelled producers in the Pilbara, Kwinana and Gladstone all processing a hematite ore with 62% iron content, while producers in the Eyre Peninsula and Geraldton are processing a higher grade magnetite. So what did we do with all of these inputs? What we did is that we used a dynamic optimization model to identify the lowest cost combination of investments and production in each location and with each technology. And so now turning to the results of that modelling, what you can see very immediately is that there is very substantial cost variation across technologies and locations. That cost variation ranges from $670 a tonne in the Eyre Peninsula and $770 a tonne for producers in Geraldton that are using a flexible technology, all the way up to about $1,400 a tonne for producers using an inflexible technology in the Pilbara. So when confronted with this level of variation, the natural question to ask is, well, what's driving it? And the first analytical insight from our model is that flexible technology is likely to substantially reduce the cost of producing green iron. And that's because the scope to ramp production up and down more easily means that producers don't need to invest in the same level of very expensive renewable energy capacity and storage to account for those periods when the sun's not shining, the wind's not blowing, and stored electricity isn't readily available. Of course, as you all know, everyone in the room here, this flexible technology is still under development with research pending to demonstrate its potential at scale. But we do find quite substantial cost variations driven by our expected capacity to seize the advantage of that flexibility. The second stylised fact is that in the early stages of a green iron industry, a connection to an existing electricity grid can reduce the cost of production. And this is for two main reasons. The first is that connected projects can benefit from the shared resources generated by other energy suppliers into the grid. But it's also because when electricity prices are high, a green iron project with renewables attached to it can sell into the grid to capitalise on those high prices and buy buy when prices are low to reduce the average cost of production. And third, a producer's location is critical. So despite the advantage of the abundant iron ore in the Pilbara, it's unlikely, or based on our modelling, it's unlikely to be one of Australia's lower cost locations, at least initially. And that's because other locations have a lower cost of capital, some advantages in existing infrastructure, and some regions also have better renewable energy capacity. And unlike the Pilbara or higher grade magnetite ore does not require smelting, which reduces the cost of production by comparison in the Eyre Peninsula and in Geraldton. Although there are those large variations in costs across locations, all locations require large investments in renewable energy, which typically represents about 60% of capital costs. So reducing the cost of renewable energy is going to be crucial to green iron and other green export industries in Australia. And actually that was discussed earlier in the presentation, Arena's focus on achieving just that. So taking a step back for a second, what this all means is that the potential is enormous. We will be able to use Australian ores to make green iron, and there are low-cost combinations of locations and technology. But market failures are, at the moment, holding back Australian green iron. The first market failure is the missing international carbon price. Because emissions from fossil fuel-based iron and steel production are unpriced, green iron isn't competing on a level playing field. The second market failure is under-provision of common user infrastructure that green export producers could use to lower their average cost of production. And the third market failure takes the form of innovation spillovers and early mover risk. So what should we do about that? At TSI, what we recommend is that to correct for the lack of an international carbon price, the government should introduce a green iron production tax credit worth $170 a tonne, inclusive of its existing $2 per kilogram hydrogen production tax incentive. In addition, the government should support early producers producing it at a commercial scale. So that's over 500,000 tonnes per annum per year. What we recommend is 2 tiers of support. We recommend that early producers using any type of green iron technology should receive support or equivalent tax grants worth up to 15% of capital costs. But the grants are worth an additional 15%, bringing that total to 30%. Should be made available for the first few users of a particular green iron technology to be deployed in Australia. With that total support, whether at 15 or 30% of total capital costs, capped at $500 million per project. And that could build on or draw from the government's existing $1 billion Green Iron Investment Fund. And federal and state governments should also support the efficient provision of common user infrastructure. So that would include, for example, suitable ports, transmission, of course, at large scale, and hydrogen pipes and storage. I'm going to leave it there. I encourage you to read our report where you'll find more detail on our recommendations. And you'll also find, of course, more detail on our research, which very clearly demonstrates that with efficient policy supports, Australia can enjoy an era of productivity and growth on the back of our remarkable comparative advantage in green iron. Thank you.
Okay, I'll continue. Thanks so much, Ingrid, for that part of the presentation. I'll now move back into a bit more about the positioning of Zesty with a bit of a recap on the technology also. So just a recap on the Zesty technology. It's an application of our platform technology that introduces hydrogen for the reduction of iron ore. It's a process that can be easily powered by renewables using no carbon-based fuel and therefore generating no carbon-based emission. It's a fines-based process operating at low pressure. It's not a fluidized bed process and operates with non-complex process control. The fines are simply introduced into the top of the process. The hydrogen is introduced into the bottom and moves upwards. The hydrogen strips the oxygen from the iron ore as it passes in counterflow. The product exiting the process is a direct reduced iron product that's consumed in downstream steelmaking processes. The indirect heating enables hydrogen to be used solely for reduction of iron, so there's no combustion of the hydrogen, and therefore the ability to achieve the minimum theoretical hydrogen consumption of 54 kilos per ton of iron is achievable. We've received really positive industry feedback validating the value of Zesty from our pilot testing to date. Pilot testing results to date have matched or exceeded key parameters being achieved by alternative processing technologies currently under development in the areas such as metallization degree, briquetting density, and hydrogen consumption, as I just mentioned. The simplicity of the technology is valued, no requirement for pelletizing and shaft furnace reduction, contributing to a lower capital and lower carbon intensity flow sheet in the future. Simple scale-up, potential to match feed rate requirements for current and future iron and steel making production complexes. These facilities may be closer to the mine for green iron production on site or in country, or if the iron is exported, these facilities may be close to the steel mill or the end user, and this offers flexibility in the size of the facilities that are needed depending on the location of the ore and the end user market. Flexibility of operations has just been mentioned quite a few times. The ability for the process to be turned down and ramped up to match the availability of renewables and interruptible grids and to contribute to grid balancing. The testing we've done today demonstrates that once you switch the feed off and you allow that product to fall through the tube by gravity and exit the process, we can ramp down and go on hold within a matter of minutes. So this enables us to avoid peak power pricing. And then when conditions are more favorable, we can ramp up also quite quickly within tens of minutes to get back online. We can keep the plant on a low power input to keep everything hot, but ramp down and ramp up very quickly. As I mentioned, also hydrogen's used solely for reduction, no combustion. This enables that target for minimal theoretical hydrogen consumption to be achieved, which is critical in terms of OpEx costs. Moving on to our business model. So our business model is to be capital light, so providing maximum flexibility and accessibility to the technology under license agreements and a royalty mechanism. Zesty will provide engineering design services for commercial scale plants. Iron and steel producers may build and operate a future Zesty facility under license. Now, this approach utilizes the supply chain and purchasing power of major global producers. So a Zesty plant may be built at lower capital intensity without the high overheads and margins retained typically by global OEMs. We envisage this strategy promotes and underpins a partnership opportunity accessible to the whole of industry and allows Zesty resources to be available to deliver continued service and support to the owner-operator for the full life cycle of the facility without the requirement to build out a capital-heavy organization managing EPC or EPCM contracts. Available market data suggests significant growth in the consumption of DRI, or direct reduced iron, via the electric arc furnace processing route as blast furnace and basic oxygen furnace processes phase out to beyond 2050 and beyond. Taking conservative assumptions supported by various public sources, 25% of existing feed into blast furnaces may be substituted with direct reduced iron or hot briquetted iron. This presents a current addressable market of 310 million tons of direct reduced iron. And although that will gradually reduce as blast furnace operations phase out towards 2050, it remains a significant opportunity over the next 25 years to reduce emissions from existing blast furnace operations. In contrast, current electric arc furnace production is expected to increase almost fourfold by 2050, from 165 million tons currently to 630 million tons as a combination of non-scrap-based steel and electric smelting furnace-derived feedstock. So combined, this presents a total addressable market potential of 790 million tons of direct reduced iron globally by 2050. My final part of the presentation is to now just talk about the progress to date with the Zesty technology. So as Phil mentioned at the beginning of the presentation, we started thinking about Zesty in 2021, and that's when we started with our initial kinetic studies. And then we achieved our first phase of pilot testing in 2022. And then in the next couple of years, we moved through the pre-feed and feed study phase, which led to the ability to design the demonstration facility. So at this point now, with feed completed, we're ready to commence the final detailed design and EPC for a commercial demonstration facility, with commissioning and operation of that demonstration facility slated for 2028 onwards. Just touching on some of the techno-economics coming out of the pre-feed. So we've done over 130 tests in our pilot facilities in Victoria, and those tests have been done across 9 different Australian ore variants that have been tested. The techno-economics coming out of the results today show that our energy consumption is around 0.9 to 1.3 megawatt hours per ton of HBI, and we can land at a levelized cost of HBI production between $390 to $500 based on the assumptions of electricity pricing that Phil mentioned earlier. We've achieved fantastic metallization results from low and mid-grade Pilbara ores producing 98% metallization. We've also briquetted those ores, and there's a shipping standard for briquetting density of 5 kilos per cubic meter. And we've been in touching distance of those of that standard with a simple first pass at briquetting the material without doing anything special or adding binders or carbon to that material. So we're already very close to that international standard for briquetting requirements. So we're highly confident that the DRI that we're producing metallizes sufficiently and also can be transported safely. The scalability of the technology is fairly simple. The demonstration plant will be a full-scale single tube, and then it's simply modular expansion from that point on. So multiple tube concepts. So the more tons, the more tubes. But the demonstration facility will be the largest tube we have to make, and we expect a lot of efficiency improvements through the demonstration plant campaign testing. The plant size to demonstrate the operation of a commercial scale single reactor tube, as I mentioned. The plant will advance TRL development in terms of process efficiency, power and utilities consumption, and production yield. For example, the facility will have a hydrogen recycle loop to demonstrate minimum hydrogen consumption. That's not been practical to test on existing pilot facilities. The plant will demonstrate continuous and intermittent operations, and the demonstration plant operations would also provide scale-up design parameters that will inform the feed study for commercial scale multi-tube modular facilities. Site locations have been assessed domestically across Australia, and we're in the final negotiations to make a call on the final site with a shortlist in place. The current state of the technology is TRL5, and the demonstration project will advance that technology to TRL7. The completion of a commercial readiness program is included in the design, and performance information from that feed study will inform the design of multi-scale future facilities. So this shows the timeline for progression to the demonstration facility. The project allows for commissioning and ramp up, leading to a 2-year operational demonstration period. We plan to commission on available hydrogen. The Zesty process is agnostic to the H2 source, so it's possible for this facility to run on grey hydrogen or renewable hydrogen, and the plant will operate on whichever hydrogen is available to allow those campaigns to take place. Operating on a campaign basis, the test plan is purposely intended to actively progress technical de-risking to inform future commercial design. A series of customer campaigns are to be targeted in order to achieve end user validation, e.g. hydrogen consumption reduction degree and product specifications. The intent is for the plant to have a continued life beyond demonstration as a commercial research and trial facility, with the capability of being adapted for the processing of other critical minerals in the future. I'd also now like to talk about the team we have in place. So I introduced myself earlier, leading the sustainable processing business at this stage in Calix. I also have Sebastian van Dorp, who's joined us in the last 8 months, who has a very strong background in iron ore and has come from major global ore companies and in technical marketing roles. And Seb's brought a significant amount of experience to the team and is engaged in a lot of international ore companies as well for potential further testing in our existing pilot facilities. Also have Ian Dunn, who joins us at the same time as Seb, comes from a background in downstream processing in global OEMs and brings a lot of valuable experience to the team as we start to roll and build the business out. We also have the pleasure of having Professor Jeff Brooks and Dr. Sarah Hornby acting as technical advisors, globally recognized academic and industry specialists, bringing great wealth of expertise as we form our initial technical advisory board for Zesty. And of course, as the project develops and we continue working with our industry partners, there's an opportunity for further technical advisors from industry to become part of the advisory board as we continue to develop the Zesty technology. And on that note, I shall hand back to Phil to wrap up. Thank you.
Excellent. Thanks very much, Chris. Want to leave a bit of time for questions, so I'll wrap up real quick. Obviously, Chris has covered off the market potential here, which is enormous. Thanks, Dr. Burford, for attendance from the Superpower Institute, outlining the opportunity here in Australia. And, despite whatever's happening in the US, that there is regionally Asia-Pac, Europe, policies that are incredible tailwinds behind this type of technology and this type of opportunity. We've got quite some advantages, we believe, to be proven, but there are some pretty unique aspects of the technology that place us pretty well competitively. And almost, as I say, we're starting to look at if we can get the cost of renewable energy down, the levelized costs, then we can start to be in the realm of economic relevance with respect to just normal scrap iron or briquetted iron. We're targeting a pretty capital light model. Once we spend this capital and prove the technology in the demonstration plant, the idea is not to build any of these ourselves. And so the idea is a licensing and royalty type technology company with an enormous global market. We've looking to raise the capital to match the ARENA funding. We're going to do this at the subsidiary level, either in financing or in equity, similar to the way that we did the Lilac technology, where we had funds coming into a special purpose vehicle to help develop the technology. And of course, those funds will be matching the ARENA funds that have been announced last week, which are after pretty thorough due diligence with respect to technical and techno-economic assessment of the ARENA. We've signed that grant agreement with ARENA. So a lot to be excited about. And at this point, let's jump into a Q&A. So let's leave some time for questions. So thanks again for your attention. Thanks, Chris. Thanks, Ingrid, for your presentations. And over to you, Christine, to manage the questions.
Thank you, Phil. We've had a few questions come in through the Q&A box and also some through my inbox. So just a reminder that if you'd like to ask any questions, please pop them into the Q&A. And if you'd like to remain anonymous, you can send them to investorrelations@calix.global. So I did receive a few this morning, so I'm going to kick off with them. And first one, and that's right, Chris, if you can be online. So the first one is often adoption of these technologies comes down to cold, hard economics. So perhaps the panel has a view on the outlook on the cost profile of Zesty relative to the current industry standard process for manufacturing steel. That is, can Zesty become cost equivalent to the existing tech?
Yeah, we believe so. As I mentioned, the predictions that we have for the cost per ton of DRI within that $400 per ton is comparable to existing commercial production without the application of a carbon penalty. There's two simple inputs into the cost of producing the DRI. It's the energy and the hydrogen for reduction. So all efforts to make energy consumption and hydrogen consumption as efficient as possible is what we aim to demonstrate with the demonstration plant, on top of the promising results we've already had at the pilot scale. So 54 kilos a ton is the minimum hydrogen you need. You can't use less. Some processes are using over 70 kilos per ton to reduce because there's an element of combustion. So technologies that can drive towards that minimum consumption of hydrogen will be lower cost because of the efficient consumption there, not being used in consumption. And then the direct heating allows us to finely tune our power input and also to be able to quickly respond to high price periods. So again, that gives us the opportunity to be most efficient on energy use also.
Thanks, Chris. Next question is, what is the outlook for the supply of hydrogen in Australia, given a number of high-profile projects appear to be slowing or even abandoned?
Yeah, absolutely. It's certainly been a journey over the last 12 months. A lot of large-scale hydrogen hub developments have paused or been cancelled. The great thing about our technology advancement is that we can prove it on any source of hydrogen. So we're working closely to be able to have hydrogen supply to feed the demonstration facility within the time frame of the project. It's a short-term issue. What's most important for us is that we prove the technology advanced through the TRL with the hydrogen that is available. And then when larger scale facilities for renewable hydrogen are available in the future, and the power and the energy price also drives down, then there'll be improved situation domestically.
Okay. Going to the Q&A box, there was a question about chemistry and the tech. So does the reduction happen on the wall of the tube or in the central space?
It's within the central space, so it's a radiant heat process. So the indirect heating from the outside radiates from the tube to create the temperature within the reactor. So it's within the void of the reactor as the product drops through the vessel.
Okay. Our next question, is there a plan to integrate the Zesty project with methane pyrolysis, HAZER, to produce low carbon hydrogen?
Yeah, that's a really interesting project development with HAZER that'll produce hydrogen available to the market, ideally at a lower cost. So as I mentioned, we can accept any form of hydrogen for the reduction. So we're interested in continued discussions with all of our partners who are looking at new hydrogen processing technologies to support technologies like Zesty.
Maybe there's a question in there for you, Phil, as well. What is the timeline to revenue for Zesty?
So we plan to build the demonstration plant within the next 2 years and be operating that facility from 2028. So first revenue streams from the demonstration facility through toll processing of ores within the next 3 years. During the demonstration project, we will commence the commercial feed study for commercial scale facilities. The natural progression from the demonstration plant would be to build the first commercial facility towards 2030 and in early 2030.
And I might add to that, Christine, as well, because in our Lilac business, which is our application in cement and lime, there's already pretty reasonable revenues being earned on engineering studies and test work studies. And so while not the ultimate prize, it certainly helps to cover costs and assist with the development process. And so as Zesty continues to develop, we'll be looking at the same revenue model, engineering studies and paid trials.
Okay, thanks, Phil. Next question is, the business model required producers to build and run the plant and take the financial risk over the viability of the solution. The initial proposal is for the government to take some of the risk. However, domestic and international producers need to step up. How progressed are discussions with producers?
We've had a number of discussions with the industry partners in Australia who've already tested our ores, and we've now expanded that to international producers. So our focus at the moment is to continue with the pilot testing, as Phil mentioned, in the existing facilities, and plan for larger volumes of material to be put through the demonstration plant. And that all paves the way for future commercial uptake of the technology. At the end of the day, we need to scale up from pilot testing. We need to move towards this demonstration facility to build the confidence, as with every emerging technology, that needs to advance through the TRL scale for commercial readiness. So we're well set to continue on that journey with our industry partners.
And I might add as well, Christine, that certainly, again, I'll draw a parallel with our Lilac business for cement and lime, where the funding that helped continue the Lilac business was through impact funds. And so while strategic interest is important, there's no doubt, and Chris has outlined the engagement to date. Certainly as well, we're looking at other models and compatible models, if you like, to finance the other half of the demonstration project from sources such as impact funds globally.
Okay. We've got a few more minutes, just a couple more questions, so I'll try and shoot them out. Does the column, I imagine the tube, need an inert atmosphere in conjunction with hydrogen to prevent oxygen input and possible explosion?
No, it's a low pressure process. There's no internal refractories. It's very simply product in the top and hydrogen through the bottom. There's a small pressure level maintained to prevent air ingress, but otherwise a very simple process. And the pilot facility has certainly demonstrated that that's highly successful, and we look forward to continuing that demonstration with the full scale single tube.
Okay, thanks, Chris. Couple more. Given the significant capital investment required, how will the Calix headstock benefit from the funding, i.e. the SPV structure used to pursue the proving and commercialization of this technology?
Yeah, I guess I can't comment too much on the market performance of the Calix headstock, but certainly the business model that we adopted for the cement and lime is the one we're looking at here with respect to the financing attribute. So we are looking at financing and or equity, if you like, into a subsidiary or special purpose vehicle. What that allowed to do when we did that with the cement and lime business was the market was able to sort of have a look through the headstock and understand how an expert impact fund, for example, was valuing the technology. And so this might be another opportunity if we're successful finding that matching funding through that mechanism. This might be another chance for the market to have a look through value on where the Zesty technology might be valued by strategics or financials such as impact funds.
Thank you. I'll just say we've got time for one last question. What would you expect key milestones to be over the rest of CY25?
So at this stage, we hope to be able to commence the detailed design for the demonstration plant within this existing period. So within the next 6 months, we'll be moving towards the detailed design phase for the project in line with the project timeline, with then the commencement of the EPC phase in early 2026.
Yeah, so certainly I'll just add to that, Kristen, our target as per the ASX announcement we put out last week is to, as Chris mentioned, before the end of this financial year, start to move into the heavy lifting part of the project. So procurement, construction, etc. That will necessarily obviously require some matching funding to the ARENA funding. But rather than talk about the calendar year, let's talk about the financial year. Our target is to start to move into that phase this financial year.
Okay, thanks, Phil. I think that's all the time we have for questions today, unfortunately. If your questions haven't been answered, we'll endeavour to come back to you directly. And if you've got any further questions, don't hesitate to send them through to investorrelations@calix.global. Thank you to Phil and Chris and to Dr. Ingrid as well for the presentation. If there's any closing remarks, I'll hand over to you both. Otherwise, we will close off the session.
I'll just perhaps close it off, Christine. So first of all, huge thanks to Dr. Ingrid Burford from the Superpower Institute. And also thanks, Chris, obviously, for taking us on that deep dive into Zesty. I hope it's been an informative presentation for you all. The presentation is on the ASX platform, so please download it, go through it. As Christine said, if you've got questions that come up, we're very happy to try and answer those questions as soon as we can. So thank you very much all for your attendance today.